In the last clip, we saw that atoms in their desire for a noble gas configuration can make the covalent bond like F2 or the ionic bond like LIF. But the truth of the matter is that most atoms, when they come together to make bonds, make a bond between the two, between covalent and ionic, called the polar covalent bond. A good example of a polar covalent bond would be the molecule HCl. You can see in the top picture, H has to some extent acquired a second electron to be like helium, and chlorine has acquired an eighth electron to be like the noble gas argon. So in some sense, it's covalent-like. But H and Cl are not the same atom. They don't have the same propensity for electrons. Chlorine is almost the last member of the third row. It therefore has an enormous amount of imperfect shielding of valence electrons, and therefore has a very high Z effective, sucking the electrons to it, while hydrogen is in the middle of its very tiny first row and can both lose and gain electrons somewhat equally. And so the truth of the matter is, in HCl, although it looks like the electron pair is being shared to a much greater extent, it is being brought over to the chlorine. And the amount that is being brought over is measured by delta. So there's hydrogen and chlorine. And the convention then is to draw a what's called the dipole moment, which is drawn as an arrow with a plus sign on one side. See that plus sign, and a minus sign on the other side. That's the dipole moment, the convention that chemists normally use. And the dipole moment is exactly defined by the equation mu. Dipole moments go by the Greek letter mu, equals d times delta. Delta is the charge difference between the two atoms, and d is the distance between the two atoms, which is conventionally drawn from nucleus to nucleus. And the important thing about the dipole moment is that it is measurable. The experimental measure of the dipole moment here is their mu experiment, 1.08 dBs, and the letter D is the dBi is the unit. It's a good one for Cornelians to know. It's the only unit that's named after a Cornell, a member of the Cornell faculty. Okay, chemists then have studied these. They can find these experimentally, the dipole moments, and they have studied them. And the larger the dipole moment, the larger delta, the larger the dipole moment, the more it's ionic, and the smaller the delta, it's more it's covalent. That's expressed in these equations. We're going to introduce the idea of the calculated mu bond, which will be it's really just if they are being is at 100 picometers at 4.8 dBs, that would be complete transfer. So if we compare this calculated mu bond to the experimental mu bond, we'll get the percent ionic character. So if you really had a mu bond of 4.8 dBs at 100 picometers, you really would have a complete transfer of 1. And so this is a very convenient way for us to get the percent ionic character from the experimental determination of the dipole moment. And so chemists have set out studying these, and the most important person who has started studying the polar covalent bond is Linus Pauling. And he looked at lots of data for it, and to understand Linus Pauling's work, this is a very important picture to understand. Here's HCl. When the two atoms are far apart, there's no bond. When they come close to each other, they make a bond. They're shown bonded HCl, and you see BDE. BDE stands for bond dissociation energy. And finally, at very short distances, the atoms start repelling each other, going up. So that's the classic picture, and we're going to need this BDE, the bond dissociated energy, to understand Pauling's work. And what he did then was he took the bond dissociation energies of the pure covalent situations, the A atom to the A atom, the B atom to the B atom. He studied the bond dissociation energies of the polar covalent atom, A to B, and he discovered that there was a discrepancy between the two called delta. And delta AB follows that equation there, and there's this Greek letter chi A and chi B, which are the electronegativities. So a large difference in chi leads to an increased energy, and this is due to the additional ionic character of the polar covalent bond. And when Pauling then came out and tried to determine what the best values for chi's were, he found this chart here. And to understand then what is chi really measuring, it's measuring two factors. Do you see lithium is 1, beryllium is 1.5, boron 2, 2.5, 3, 3.54. That's just the approximate increase of Z effective. So one factor is going from left to right is the imperfect shielding of valence electrons. And the second factor is you see as you go down the columns, it's getting the Pauling electronegativity is getting smaller, and that is due to the fact that N is increasing, and therefore the total energies are becoming smaller.